Hello, good evening everyone. Welcome to Gradeup. I am Vikas Bhadoria and I welcome you all again in the live session on Thermodynamic Revision Part 3 under GATE 2020 Score Booster Series. As you all know that this Score Booster Series is going on the YouTube channel for those students who are preparing for the GATE exam from the last 1 year, 6 months, 3 months, 2 years, 2 months. Okay, so for those students, this is a revision series, and in that we total had 3 sessions. This is the third session on thermodynamics. Okay, in the first 2 sessions we have revised the complete subject of thermodynamics and IC engine, and in this session we are going to revise the complete important topics of refrigeration, air conditioning and power plant. Okay, so I welcome you all in this session. Very good evening. I will be waiting for you to join the session and then we'll start it. Good evening, Saurabh. Good evening, Pawan Kalyan. Hi, good evening, Pawan. I think if you are the same Pawan who is in the rank up gate AMI, then very good evening to you, because Vinayak, good evening Vinayak. Yes, so good evening to all of you and I welcome you all in this session. We total had 2 sessions till now in the thermodynamic revision, and today is the third session under the same series, Score Booster Series. This is specially for those students who are preparing for the GATE exam from the last few months, years. Okay. Yes, Pawan, I am very good. Good evening, Ankit Kumar. Good evening, Akshay Singh. Good evening to all of you. So today is the final session on thermodynamic revision. Till now we have completed the revision of thermodynamics and IC engine. And now we are going to revise the subject of refrigeration, air conditioning and power plant. Okay. So good evening all of you. So I think right now we have total 27 students I can see live right now in the YouTube. So I think we can start it. Yes, good evening to all of you, those who have joined the session. So let's start. Now, this is a brief introduction about me. Those who don't know about me, especially this is for those students, okay, who are meeting me for the first time. My name is Vikas Bhadoria and I have 5+ year teaching experience, and I did my M.Tech in thermal engineering, mentored this much amount of students, and area of expertise includes fluid mechanics, thermo applied and heat transfer. Okay, that is a brief information about me. Now, this is a very important information. Those students who are preparing for the GATE exam from the last few months or year, only 24 days are left for the GATE 2020, and that is why we are having this revision series for you all. And so 24 days are left. It's time to just revise all your concepts, all your formulas, and practice your mock tests. That is the only time left. It's not in this time you should not take a new subject or new topic. It's better to revise everything that you have studied so far. Okay. Before we start this is a very important information. I hope most of you already taken this ISRO Mega Mock Challenge. This was started from today onwards. That is from 8 Jan at 12 p.m. Okay, so those who have not registered for this, or those who have not taken this Mega Mock Challenge, the time it's still going on till 9th of Jan 12 p.m. Okay, so those who are preparing for the ISRO exam on 12th of January, you can attempt this Mega Mock Challenge. Okay. It's live on our Gradeup app. Okay. So let's come to the revision of refrigeration, air conditioning and power plant without wasting any time, because time is very much important and we should not waste it. So good evening Vikram Singh, he's in the app. So in the refrigeration, air conditioning, what is the important topic is refrigeration effect. What is refrigeration, air conditioning? In that we will be studying about different types of refrigeration system. Like vapor refrigeration system, in that we have studied vapor compression, vapor absorption system, gas refrigeration system and psychrometry. Okay, so what is refrigeration effect? It is the process of providing and maintaining lower temperature as compared to surrounding. That is the definition of refrigeration effect. Okay, and for all the devices, for all the refrigeration devices, the coefficient of performance is used to measure the performance of these devices, and it is defined as the ratio of the desired effect to the work input, already explained to you in the subject of thermodynamics, right? It is defined as the ratio of desired effect over work input. Okay. Now the unit of refrigeration is defined as, what is the unit of refrigeration? It is called tons of refrigeration. Unit of refrigeration is tons of refrigeration, and it is defined as the amount of heat which is required to extract from 1 ton of water at 0 degrees Celsius in order to convert it into ice at 0 degrees Celsius in a day or 24 hours. Okay, and it is represented by symbol TR, which is called tons of refrigeration. And 1 TR is equal to 3.5 kilowatt or 210 kilojoule per minute or 50 kilocalorie per minute. That is the unit conversion of 1 ton of refrigeration. So it's up to you, and it depends on the exam that what has been asked in the exam. If they will be asking you to find the value in kilowatts, so it will be 1 ton of refrigeration will be 3.5 kilowatt or 210 kilojoule per minute or 50 kilocalorie per minute. Okay. Now, under vapor refrigeration air conditioning, this topic has already been covered in the second law of thermodynamics. But under refrigeration air conditioning also under reverse Carnot cycle, because heat pump and refrigerator both are based on reverse Carnot cycle. What is reverse Carnot cycle? When Carnot cycle acts in anti-clockwise direction, it is called reverse Carnot cycle. So these heat pump and refrigerator are based on reverse Carnot cycle. So either you understand the concept of heat pump and refrigerator in the subject of thermodynamics, in second law of thermodynamics, or you understand in the subject of refrigeration air conditioning. It's totally up to you. Okay. So under this heat pump and refrigerator, you know that if you see the application of heat pump and refrigerator, basically there are two applications, heat pump and refrigerator. So if you see, this is suppose this is a refrigerator and this is a pump. Okay. Now what is the difference? Only thing that you have to remember is coefficient of performance of a refrigerator and heat pump is equal to desired effect over work input. Because both of these devices are almost same, they both take the work as input, and utilizing that work, refrigerator is used to maintain a system at lower temperature as compared to surrounding, and heat pump is used to maintain a system at higher temperature as compared to surrounding. Okay, so that is how these two devices work, and the coefficient of performance is equal to desired effect over work input. For a refrigerator, this is equal to, for a refrigerator, this will be equal to, in this case, suppose this is a refrigerator, so this will be equal to Q1 over Q2 minus Q1, and for a pump or heat pump, this will be equal to Q2 over Q2 minus Q1. Suppose the cold body is having temperature of TL and hot body is having temperature of TH. So in the case of refrigerator, this COP will be equal to TL over TH minus TL. That will be the formula for COP of a refrigerator. And for a heat pump, this will be equal to, heat pump will be equal to TH over TH minus TL. Already explained this thing, so I will not be taking much time on that. Okay. Now there is a relation between COP of the heat pump and refrigerator. That is, COP of the heat pump is equal to 1 plus COP of refrigerator. So this is also very important. COP of heat pump is equal to 1 plus COP of refrigerator. Okay. So this relation is very important, and this is the formula for finding the COP. Okay. So in this, you just have to remember the formula of COP. It is equal to desired effect over work input. So for calculation purpose, you have to remember that you have to keep desired effect. Whatever is the cycle, they will be giving you the value of work input, they will give you the value of desired effect, or either they can ask you the value of desired effect or power input. Okay, so you have to remember this formula of COP. Okay. Now, under refrigeration air conditioning, there are two types of refrigeration system: vapor refrigeration and gas refrigeration. Under vapor refrigeration, we have vapor compression refrigeration system and vapor absorption refrigeration system. So it basically, vapor compression refrigeration system is based on the concept of compressing the vapor to produce the refrigeration effect. And basically it contains four important components. First one component is compressor, then we have condenser, then we have expansion valve and evaporator. Okay. So since it is a refrigeration system, it will act in the anti-clockwise direction because all the refrigeration system act in the anti-clockwise direction. Okay, so firstly we will have compressor, it will compress the refrigerant vapor from the evaporator. That saturated vapor will get compressed in the compressor, that is the function of compressor. Then that it will increase the temperature and pressure of the refrigerant vapor. Then this refrigerant vapor will go into the condenser. What is the function of condenser? Condenser function is to reject the heat. Okay, because it is a heat exchanger which reject the heat. Okay, so it will reject the heat. Okay, then this when the heat rejection will take place, it is a condensation. Condensation phenomena means conversion of vapor into liquid. Okay, so in the condenser what will happen when condensation will take place, the vapor will change into liquid and also the temperature will also drop. So if what will happen here, the saturated liquid will pass into expansion valve or throttling valve. Now in the case of a vapor compression system, we will be using a expansion valve or throttling device. Okay, now the throttling device normally we use in the refrigeration system is a capillary tube, or it can be automatic expansion valve or thermostatic expansion valve. Okay, so this why we use expansion valve in the case of vapor compression system, because the work which we require for expansion is not that much as compared to the purpose. The purpose is to just decrease the temperature and pressure of the saturated liquid, and that can be easily fulfilled with the help of a small expansion device. Okay, so that is why we don't use an expander in the case of vapor compression system. We only use an expansion device called as throttling device. Okay, so what will happen? This is based on expansion, so the enthalpy at this point will be equal to enthalpy at this point because it is a throttling device. Okay, so now this the saturated liquid vapor will go into the evaporator. What is the function of evaporator? Evaporator is the main device in the vapor compression system which performs the function of keeping the system at a lower temperature. Okay, so in the evaporator, heat will be added in the evaporator, and when heat will be added in the evaporator, what will happen? This evaporator will convert the saturated liquid into saturated vapor, and this vapor will go into the compressor again. This is how the cycle will continue. Okay. If you see this vapor compression system on a PV and TS diagram, pressure, enthalpy and temperature entropy diagram, this looks like this. Okay, so you have to remember both the diagrams. Okay, so this is a diagram of temperature entropy of a vapor compression system. You can see this 1 to 2 is compression, then we have heat rejection in the condenser, then we have throttling process. Now you can see here the throttling process, since it is this is a throttling process. This will not be throttling. So this is the throttling process 3 to 4, and then we have 4 to 1. Okay, heat addition in the evaporator. Similarly, you can see this process on the in the case of pressure enthalpy curve. Pressure enthalpy curve, both the diagrams are important. So this is a temperature entropy, this is pressure enthalpy curve. Okay, now if we have to measure the COP of this vapor compression system, the COP is equal to refrigeration effect over work input. You have to remember this formula, or it is equal to refrigeration capacity over power input. Now you must be thinking, what is the difference between refrigeration effect and work input, and why I am writing it is equal to refrigeration capacity into power input. It is nothing, there is no difference. Only difference is that here in the refrigeration effect you have to multiply with mass. You just have to multiply with mass. Okay, if you multiply with mass in the numerator and denominator, you will get refrigeration capacity and power input. That is the only difference. So both the formulas you have to remember. Okay, so if you see this present diagram, what is refrigeration effect? Refrigeration effect is only produced in the evaporator. Okay, so refrigeration effect we are getting only in the evaporator. So this will be equal to H1 minus H4. What is work input? Work input we are only provided with the help of compressor. Okay, so this will be equal to H2 minus H1. So that is the formula of COP. If directly in the exam you will know the value of H1, H4 and H2, H1, you can easily put the values in this formula and you will get the answer. Understand? So you just have to remember this formula for a vapor compression system. If you have to find the COP of a vapor compression system, you just have to remember this formula. You just need to find the enthalpy values at the given points, at the inlet of the evaporator, at the exit of the evaporator, or at the inlet of the compressor, at the exit of the compressor, and at the entry of the evaporator. These enthalpy values you have to find just to calculate the value of COP. Okay. So that is a very important formula. Don't forget this formula in the exam. Now let's come to sometimes this question may be asked in the theory that why we are using wet compression. What is the difference between wet compression and dry compression? See, wet compression, dry compression are, if you see wet compression, what is the meaning of wet and dry compression? So you know that after the evaporator sends saturated vapor into the compressor for compression. Now see, we know that compressor, what is a compressor? Compressor is a device which compresses the vapor, right? Now if vapor does not go into the compressor, if liquid and vapor both goes into the compressor, then what will happen? Then it will cause problem in the blades of the it can cause erosion problem on it, and if that liquid refrigerant goes into the evaporator, it can cause choking of the evaporator. Okay, so to remove that problem, we should only compress saturated vapor in the compressor. It should not contain liquid refrigerant, it should only contain vapor refrigerant. Okay, so the difference between wet and dry compression is that when we compress only vapor refrigerant, it is called dry compression, and when we compress the mixture of liquid and vapor both, then it is called as wet compression. So wet compression is never desired. Why? Because first problem is that it can cause leakage of the refrigerant oil, leakage of the refrigerant or leakage of the oil which is present in the compressor, and that oil when goes into the evaporator, it can cause choking of the evaporator. Okay, and the second problem is that if you see this wet compression, suppose this wet compression means compression from this point. Suppose this is a point 1 dash, and if you compress from this point, what will happen? First thing that will happen is the refrigeration effect will decrease. Refrigeration effect will decrease. Refrigeration effect is this much now. Initially for dry compression, it was this refrigeration effect. Due to wet compression, refrigeration effect has decreased. So that is why we should always have dry compression as compared to wet compression. Okay. So these points are written here. Wet compression means incomplete evaporation of the refrigerant, hence refrigeration effect decreases. It is difficult to compress the liquid vapor mixture. The liquid particles might wash away the refrigerant and thus increase wear and tear. And they have written the volumetric efficiency formula. Volumetric efficiency formula is important. Volumetric efficiency is equal to mass, actual volume at the inlet of the compressor divided by swept volume. That is equal to pi by 4 d square into L into N into K divided by 60. That is the formula of volumetric efficiency of a compressor. So you have to remember this formula. Okay. Volumetric efficiency we have learnt in the lecture of this IC engine, that it is equal to ratio of the actual volume entry into the compressor over swept volume. Okay. So actual volume will be equal to what? Mass of the refrigerant into a specific volume at the entry of the compressor. Divided by swept volume is equal to pi by 4 d square L and K by 60, where K is the number of cylinder in the compressor, N is the RPM of the or speed of rotation of the motor in the compressor, L is the length of the stroke, D is the diameter of the cylinder. So that is the formula you have to remember for volumetric efficiency. It is important. Okay. So maybe sometimes direct question comes from volumetric efficiency. So you have to use this formula. Okay. Now, if you see this vapor compression system, there are some theory question also comes in the exam. Directly theory question comes that if we change the evaporator pressure or the condenser pressure, or we conduct superheating or subcooling, then what is going to happen on what will be the effect on the coefficient of performance or COP. So these effects are written here. First effect is effect of variation of evaporator and condenser pressure. So the effect it is given here is for increase of condenser pressure and decrease of evaporator pressure. If we increase the condenser pressure and decrease the evaporator pressure, then what will happen? So these affect the changes will be this is which is written here. So the major changes will be, it will be having a decrease in the refrigeration effect, okay, increase in the work input, decrease in the COP, and decrease in the volumetric efficiency due to increase in pressure ratio. Now how we are saying this? Because volumetric efficiency is having this formula. It is equal to 1 plus C minus C, higher pressure over lower pressure, power 1 by n. This is also a formula for volumetric efficiency of a compressor, okay, where C is called as clearance ratio. Clearance ratio, which is equal to ratio of clearance volume over swept volume. Okay. So this is a very important formula. Now if you see, Kathan Shah is saying in VCRS, subcooling causes increasing in COP and volumetric efficiency, and superheating cause increase or decrease in COP. Kathan Shah, I'm coming on that. I'm coming on the topic of subcooling and superheating. Okay. So, so whenever these two things take place, whenever there is an increase in condenser pressure or decrease in evaporator pressure, this effect will take place on the refrigeration effect. There will be a decrease in refrigeration effect. And whenever decrease in refrigeration effect and increase in work input take place, COP will decrease. Okay, and also volumetric efficiency will decrease because of increase in pressure ratio. Okay. Next is the effect of superheating. What will be the effect of superheating? If you do superheating in the evaporator, then what will happen? It will cause increase in refrigeration effect. It will cause increase in work input also. Now, both we know that COP is equal to refrigeration effect over work input. Now, if both the things are increasing, what will happen to the COP in the case of superheating? In the case of superheating, in that case, COP will depend on the type of refrigerant. Okay, so the type of refrigerant, yes, this question was asked in the ESC exam also, in AC 2020 exam also. Very good. So, what is the effect of superheating? It depends on the refrigerant. So, COP may decrease, increase or decrease depends on the refrigerant. For R12 refrigerant, COP will increase, whereas for ammonia refrigerant, COP will decrease. Okay, so it will depend. In this particular case of superheating, the COP may increase or decrease. It depends on the type of refrigerant. In the case of R12 as a refrigerant, it will cause increase of COP, and for the case of ammonia as a refrigerant, COP will decrease. Okay, understand everyone? Now, next is effect of subcooling. Always remember this thing. Subcooling means lowering the temperature. So, when the lower temperature is decreased, so what will happen? Refrigeration effect will always increase. But there will be no change in the work input, and COP will always increase. Okay, that is the very important thing, that subcooling always increases the COP. If subcooling is taking place, COP will always increase. Okay. Now, this thing is sometimes also asked that what is the effect of flash chamber? What is the function of flash chamber? I have told you this thing that there is a problem of wet compression and dry compression. So, this wet compression, dry compression is a problem. So, how to overcome this problem of wet and dry compression? This can be avoided with the help of a flash chamber. Now, flash chamber is a device which separates the liquid and vapor refrigerant. This flash chamber device is always kept before the evaporator, so that only, after the evaporator, so that only vapor refrigerant goes from the, one thing. So, this flash chamber is a device which is used to separate the liquid and vapor refrigerant. Now, you must tell me where this device should be kept. After the expansion from the throttling device, it gives you the mixture of liquid and vapor refrigerant. So, in the evaporator, if we only provide the vapor refrigerant, it will be very easy to compress that. Right? It will be easy for the evaporator. Okay, so what we do, we'll keep the flash chamber after the evaporator, so that only vapor refrigerant goes into the compressor. Okay, but thermodynamically there is no change in the COP. There is no change in the COP if we provide the flash chamber. There will be no effect on the COP. So this is very important. Thermodynamically, there is no change in the COP with the use of flash chamber. Okay, it is just used to separate the liquid and vapor refrigerant. Now, next type of refrigerant is, others is telling that sir, fluid mechanics revision classes. Others fluid mechanics revision classes will be in the next week. Okay, so you have to wait till 15th of January. So from 15th of January onwards, we will be taking the fluid mechanics revision. Okay. Now, next refrigeration system is vapor absorption refrigeration system. In the vapor absorption refrigeration system, only difference is that it is called as heat refrigeration system. Why it is called heat refrigeration system? Because in the case of vapor compression, we were using the compressor. We were using the work input by compressor to compress the vapor. But in the vapor absorption system, we have removed the compressor and we are using 3 devices in place of compressor, that is absorber, pump and generator. So we have replaced the compressor with these 3 devices. Okay. Now, that is the working. I'm not going to explain the working of this. You just have to remember that in the vapor compression system, we are using a compressor. In vapor absorption, we are replace the compressor with 3 devices: absorber, pump and generator. Okay, rest everything is same. Only difference is that since all these 3 devices are heat operated system. Okay, absorber also reject the heat, generator heat is supplied. So it is a heat operated refrigeration system. And this refrigeration system is used where the cost of electricity is very, very high. Where we cannot afford the electricity, there we use this vapor absorption system. Okay, or where the cost of electricity is high, or where we don't have sufficient electricity at most of the time, where there we use vapor absorption system. Mainly in Rajasthan, and the example of vapor absorption system is Electrolux refrigerator. Electrolux refrigerator is a refrigerator which is based on vapor absorption refrigeration system. And also in solar refrigeration system, in solar refrigeration system, we use vapor absorption refrigeration system. Okay. Now, if we, how the question comes in the exam? The question in the exam can come as a theory question, that the COP of vapor absorption system is always less than the COP of vapor compression system. Why? Because the COP of a vapor compression system depends on the work input. Okay, so it will be having more COP, more coefficient of performance as compared to the value of COP of VRS. Now, how to calculate the COP of a VRS, vapor absorption system? So in the exam, whenever you have to find, we have to find the COP of a vapor absorption system, you just need to find 3 temperature. First temperature is generator temperature. Generator temperature let us say it is Tg. Then you have to find the evaporator temperature. Now you can easily find this temperature, right? Because generator temperature is the highest temperature and evaporator temperature is the lowest temperature, right? You can easily find these 2 temperature from the question, right? Now the third temperature that you have to find the COP is, it is the surrounding temperature. That will be also given in the question, surrounding temperature. Suppose, let's say it is equal to T0. Okay. Now if you have to find the COP of this vapor absorption system, you just have to use a single formula, that is COP of a vapor absorption system is equal to QE over QG, that is heat which is supplied by the evaporator over heat supplied by the generator, which is equal to 1 minus T0 by Tg into Te over T0 minus T. So this formula you have to use to find the COP of a vapor absorption system. Now, let us understand this thing. In the case of a vapor absorption system, I have told you have to find 3 temperature. First temperature, generator temperature, evaporator temperature and surrounding temperature. Okay, after finding these 3 temperature, you just have to put this temperature in this formula and you will get the answer. Now this formula is nothing. It is just we have applied between generator and surrounding, we have used a heat engine formula, and between evaporator and surrounding we have used the formula of a refrigerator, and you have got your COP. Okay. Sadhu Kumar, what is terms of refrigeration, I have explained in the beginning of this lecture. So after the session goes off, you can watch that. Okay. Yes, in the case of a Electrolux refrigerator, we don't use a pump, and that is the advantage of a Electrolux refrigerator, because we don't use pump, so it is a noiseless operation. Okay. If we don't use a pump in the vapor absorption system, it will be noiseless operation. So that is a good thing. That is the advantage of Electrolux refrigerator. Okay, but we use in that we use ammonia as a refrigerant and water as an absorbent and hydrogen for reducing the pressure. Okay. Now next is gas refrigeration system. Gas refrigeration system. gas refrigeration system is another type of refrigeration system. Why it is different from vapor refrigeration system? Because in the vapor refrigeration system, we were compressing the, yes, what is this E go over GOE? I don't understand that formula. You have devised your own formula. Okay, so let us understand this thing. Vapor absorption system were producing the refrigeration effect. This topic is not in the GATE syllabus. Well, AUW, if you think this topic is not in the GATE syllabus, you can see the previous year questions, and you can just find it from the previous year question that the question comes from gas refrigeration system. Okay, and if you think this topic is not in the syllabus, you can ignore this topic. Okay. So gas refrigeration system is another type of refrigeration system in which the refrigeration effect is produced by compressing the gas. In this, the working fluid is a working fluid that we use in ideal gas. Okay, so that is why it is called reverse working cycle is called reverse Brayton cycle. Why? Because in the Brayton cycle is the cycle for gas power plant, and since this it is a refrigeration system, it is working in the anti-clockwise direction, so it is called as reverse Brayton cycle. Okay, so it will be using through four process. Two isentropic process, and two isobaric process. Okay, so firstly we will have isentropic compression of the vapor, and then we will have heat rejection at constant pressure, and then we have then expansion, isentropic expansion. We in this gas refrigeration system will be using an expander in place of a throttling device. Okay, because the work that we require for this, we have to the work that we require for in the case of gas refrigeration system is very, very high as compared to vapor compression system. Now there are two reasons that why we are using an expander in the gas refrigeration system. The first reason is that in the gas refrigeration system we cannot use a throttling device. Why we cannot use a throttling device in the gas refrigeration system? Because throttling means enthalpy is equal. Suppose, what is the meaning of throttling? Enthalpy is equal, so enthalpy is same. And in the case of a ideal gas, in the case of a gas refrigeration system, the working fluid is an ideal gas. And for an ideal gas, enthalpy is a function of temperature. Right? So if we use a throttling device in the case of a gas refrigeration system, it will not fulfill the purpose of reducing the temperature and pressure. Because expander, what is the purpose of expander? It expands the vapor, and in that case what will happen? The pressure and temperature reduces. But if we use a throttling device, temperature will remain same, because throttling means enthalpy is same, so temperature will be same. So that is why we don't use a throttling device in the case of a gas refrigeration system. We use a expander. Okay, we use a expansion device. So if we have to find the coefficient of performance, one second. So coefficient of performance will be equal to 1 minus heat rejected over heat supplied. That with the sorry. It will be equal to refrigeration effect. Refrigeration effect is produced in the heat supplied is equal to heat supplied over net work. Okay, so that will be heat supplied over net work. Net work is equal to compressor work minus turbine work. So here this will be net work is equal to compressor work minus turbine work, because compressor here the compression work is more as compared to turbine work. So this will be compression minus turbine work. So that will be heat supplied over heat supplied minus heat rejected. Sorry. Okay, and the direct formula for COP will be equal to 1 by Rp power gamma minus 1 over gamma minus 1. That is the formula for COP of a gas refrigeration system. In this, Rp stands for pressure ratio. Okay, this pressure ratio is equal to P2 by P1, and this is also equal to P3 by P4. Okay, so you just have to remember this formula for finding the COP of a gas refrigeration system. It is equal to 1 by Rp, that is pressure ratio power gamma minus 1 over gamma minus 1. Okay. Now this is also a formula that we have to use. It heat rejection ratio, it is equal to heat rejected in the condenser divided by refrigeration effect. And this is a direct formula of heat rejection ratio, which is equal to 1 plus 1 by COP. So these two formulas are also very important. Heat rejection ratio is defined as the ratio of heat rejected in the condenser divided by refrigeration effect, and it is also equal to 1 plus 1 by COP. Now, in the in the refrigeration air conditioning subject, the most important topic is psychrometry. Like vapor refrigeration system, it is also very important topic. Now, what is psychrometry? Till now, we have understood the concept of refrigeration. In psychrometry, you will understand the air conditioning. So, psychrometry will be studying the conditioning of the air, that is about how to maintain the quality of the air, how to maintain the purity of air, how to maintain the temperature of the air. That is all we are going to study in the psychrometry. So, psychrometry is a branch of science that deals with the study of properties of moist air. Okay, now what is a moist air? Moist air, as the word suggests, moist air, the air which contains some moisture. Okay, it is not completely dry. It contains some moisture, that is why it is called a moist air. So we can say that moist air is the sum of, like it is mentioned here, it is the sum of dry air plus water vapor. Okay, so when in the air, if the air contains both dry air and water vapor, that is moisture, it is called as moisture. So in psychrometry, we have to study the simultaneous control of temperature and the purity of the air, quality of air and moisture. That is all we are going to study under psychrometry. Is negative power in Rp or what? J, if you are talking about gas refrigeration system, you know that in the gas refrigeration system, that net work will be negative work because we are supplying the network. So that is why I have written here is because it is a negative work, we know that net work is equal to turbine work minus compression work. But since we are talking about gas refrigeration system, which actually takes work as input, and input, if work is input, so this will be minus, it will be negative. So it will give you compressor work minus turbine work. Okay, because in the case of a gas refrigeration system, net work will be negative because we are supplying work to the system. That is why it will be compressor work minus turbine work. Okay. Now, there are some psychrometric terms which are important. There are direct formula which are important. So you have to understand this formula. These psychrometric terms are specific humidity. The direct formula, it is equal to ratio of mass of the vapor divided by mass of the dry air, which is equal to 0.622 PV, that is partial pressure of the vapor, divided by total pressure minus partial pressure of the vapor. That is the formula for specific humidity. And this formula is very important. So you have to remember this formula. The unit of specific humidity is kg of water vapor over kg of dry air. That is the unit of specific humidity. Okay, or it can also have the unit of gram of water vapor or gram of dry air. But what is important is you have to remember the formula of specific humidity, that is 0.622 PV over P minus PV. So this formula is important. Okay. Now another psychrometric term is called relative humidity. So specific humidity tells us about the actual amount of moisture present in the air. That is meaning of specific humidity. But what is relative humidity? Relative humidity is defined, tells us about the moisture absorbing capacity. That is called as relative humidity. So relative humidity is defined as the ratio of mass of water vapor divided by mass of vapor under saturation condition. What is saturation condition? Saturation condition is that condition in which the vapor completely gets saturated, in which you cannot, if you add something under saturation condition, it is not going to change the state of matter. That is called as saturation condition. Okay, so relative humidity is defined as the ratio of mass of vapor under normal condition divided by mass of vapor under saturation condition, or it is equal to partial pressure of the vapor or partial vapor under saturation condition. Okay. Like this, we have three things that you have to understand. Like these psychrometric terms, you have to understand this three temperatures. One is dry bulb temperature, wet bulb temperature, and dew point temperature. So dry bulb temperature is the temperature that we of the dry air. It is called dry bulb temperature. Okay, that is can be measured by ordinary thermometer. Wet bulb temperature is the temperature which is measured by covering the bulb of the thermometer with a wet cloth. Okay, then it will give you wet bulb temperature. Okay, it determines the moisture content in the air. Wet bulb temperature determines the moisture content in air, that is called wet bulb temperature. And the third temperature is dew point temperature. Dew point temperature, as the word suggests, dew. Dew means when condensation phenomena take place, at that point the temperature is called as dew point temperature. But you have to remember this thing, for an unsaturated air, the air which is not saturated, dry bulb temperature will always be greater than the wet bulb temperature, and wet bulb temperature will always be greater than the dew point temperature. Okay, but under saturation condition, these three temperature becomes equal. Under saturation condition, all these three temperature becomes equal and relative humidity becomes 100%. Okay, so these are some important things that you have to remember for your GATE exam. Next term is wet bulb depression. Wet bulb depression is equal to difference of the dry bulb temperature. It is equal to difference of the dry bulb temperature minus wet bulb temperature. That is called as wet bulb depression. Now, what is dew point temperature? Dew point temperature is the temperature corresponding to partial pressure of water vapor. What is the meaning of this thing? Partial pressure of the water vapor means PV, corresponding to this PV, the temperature that we get is called as dew point temperature, or corresponding to dew point temperature, the pressure is equal to partial pressure of the water vapor. That temperature is called as dew point temperature, corresponding to which you will get this value of PV. So the value of PV that you write in the formula of specific humidity, yes, you guys are having your own questions. When the gas does adiabatic work, its internal energy drops in closed system and enthalpy drops in open. Sadhu Kumar, that is not the thing that we are discussing right now. We are discussing psychrometry, so let's focus on that. Okay. So dew point temperature corresponding to partial pressure of the water vapor. So you have to remember this formula. And the next thing is, what is degree of saturation? Degree of saturation determines the percentage humidity. The percentage humidity is equal to degree of saturation. It is defined as the ratio of specific humidity over specific humidity under saturation condition. And the direct formula is equal to phi. Phi means relative humidity into P minus PVS over P minus PV. So degree of saturation is equal to PV over PVS into P minus PVS over P minus PV. That is the formula of degree of saturation. Well, normally this formula has not been asked so far in the exam, but you have to keep this, you have to remember this formula. Maybe this formula can be asked in the exam for degree of saturation or percentage humidity. Okay. Next, this formula is important, enthalpy of the moist air. What is the formula for enthalpy of moist air? That is equal to 1.005 into T. T is called as dry bulb temperature plus specific humidity into 2500 plus 1.88 into dry bulb temperature. That is the formula for enthalpy of the moist air. Okay. And in this formula, T is called dry bulb temperature and W is called as specific humidity. Okay. Now, in the case of psychrometry, there are some psychrometric process. To understand the psychrometric process, you have to understand some points in the psychrometric chart. So, with the help of a psychrometric chart is that chart from where you can read these psychrometric terms. So, these psychrometric terms are dry bulb temperature, it can be wet bulb temperature, it can be dew point temperature, specific humidity, relative humidity, enthalpy, specific enthalpy, that these are called as psychrometric terms. Okay, so that psychrometric terms are represented on a psychrometric chart. This looks like that. Sorry, this is how the psychrometric chart looks like. Okay, so in that psychrometric chart, we have constant dry bulb temperature line, which looks like this. These are vertical lines like this on the psychrometric chart. Okay, so these dry bulb temperature are the vertical lines. They are uniformly spaced. They increase in this direction. So in this direction, dry bulb temperature will increase. Okay. And generally scaling of 5 degrees Celsius is provided. In the psychrometric chart, each dry bulb temperature is separated by 5 degrees Celsius. Okay. Next is constant specific humidity lines. Constant specific humidity lines are the horizontal lines which are parallel to each other on the psychrometric chart. These are called as constant specific humidity lines. These are the horizontal line moving towards the saturation curve. This is the saturation curve. Saturation curve. What is the meaning of saturation curve? At this point, all these three temperature, dry bulb temperature, wet bulb temperature and dew point temperature will become equal, or relative humidity is equal to 100% at saturation curve. Okay, so the lines which move toward the saturation curve and parallel to each other like this, these are horizontal lines, these are called as specific humidity lines. Okay, and they increase in this direction. In this direction, it will increase. Okay. Next, we have constant dew point temperature line. These are also these are line, horizontal line, these which increase in this direction. Okay. Constant relative humidity line. Relative humidity lines are shown by this. These are, in this inclined line, this curve line which are parallel to this curve of saturation curve are called as relative humidity lines, and they increase in this direction. Okay. So here the relative humidity will be less as compared to at this point, because at this point relative humidity is 100%. Okay. Next, we have enthalpy, specific volume, or white bulb temperature line. These are also shown on the psychrometric chart. Okay, so how you can distinguish this specific with the help of unit, you can distinguish these lines. Why we are writing all these three lines together? Because this specific enthalpy lines, specific volume lines, and wet bulb temperature lines, all these three lines are, if you see a psychrometric chart, they will look like same. They will exactly look that these lines are looking very exactly similar. Okay. So what is the difference between these three lines? Enthalpy lines, first thing is to distinguish is the unit. You can distinguish these lines with the help of unit. Second is highest inclination lines are called as specific volume lines. Specific volume lines are inclined lines which have highest inclination. Okay. Enthalpy lines is shown outside the psychrometric chart. In the psychrometric chart, the enthalpy lines are always shown outside the psychrometric chart. And enthalpy and wet bulb temperature have same degree of inclination. But enthalpy lines are uniformly spaced, wet bulb temperature lines are not uniformly spaced. Okay. Now there are some psychrometric processes that you have to understand. There are basically four basic psychrometric processes: sensible heating, sensible cooling, humidification and dehumidification. What is the meaning of this psychrometric process? Sensible heating means when we increase the temperature, when we increase the dry bulb temperature at constant specific humidity, that is called sensible heating. When we decrease the dry bulb temperature at constant specific humidity, that is called as sensible cooling. And humidification means at constant dry bulb temperature, if you increase the specific humidity, that is called as humidification. At constant dry bulb temperature, if you decrease the specific humidity, that is called dehumidification. So these four processes are represented like this. So this is sensible heating. If you go at constant enthalpy, constant specific humidity, if you increase the dry bulb temperature, like in this direction, that is called sensible heating. So what is the effect of sensible heating? The specific humidity will be constant, dry bulb temperature, dew point temperature will be constant, specific enthalpy, specific volume, wet bulb temperature and dry bulb temperature, this is going to be increased, only relative humidity is going to decrease. That is the effect of sensible heating. Next is sensible cooling. Whatever is the effect of sensible heating, the opposite effect will take when sensible cooling will take place. Sensible cooling is in the opposite direction. If you move in this direction at constant specific humidity, that is called as sensible cooling. Then we have humidification. Humidification, like I told you, at constant dry bulb temperature, if you increase the specific humidity, that is called as humidification, or we are increasing the moisture in the air. What is specific humidity? If we are increasing the specific humidity, we are actually increasing the moisture. Okay, so humidification means increasing the specific humidity or increasing the moisture at constant dry bulb temperature. Okay, and that is dehumidification. If you go in the vertical direction and decrease the specific humidity at constant dry bulb temperature, that is called dehumidification. Okay, now if you represent all these four processes on a single chart, this looks like this. So this is humidification, then dehumidification, sensible cooling, sensible heating. Sensible heating, sensible cooling, humidification and dehumidification. But these are the four basic processes. If you see the actual refrigeration air conditioning, we don't use these four basic processes, we use combination of these four processes. So we'll have total 8 processes. That is heating and humidification, heating and sensible cooling and humidification, sensible cooling and dehumidification, and sensible heating and dehumidification. So these are total 8 psychrometric processes. Okay. So this is another term called apparatus dew point. Apparatus dew point is basically the dead temperature when the sensible cooling and dehumidification line, this line is called sensible cooling and dehumidification line. If this line touches the saturation curve, if this line touches the saturation curve, so the point where it touches the saturation curve is called as apparatus dew point temperature. Okay, so when this sensible cooling and dehumidification line will touch the saturation curve, at that point we will get the apparatus dew point temperature. At that point the vapor will start to condense. Okay, that is called. Sir, after this revision question is there. No, Pawan Kalyan, we will not be discussing the question, only we will try to cover the discussion of the topics and formulas. Because it's not possible to cover the question as well as discussion of the concept and formula in 1 or 1.5 hours. Okay, so we will not be discussing any question in this session. We will only be discussing the theories. Okay, we will only be discussing the concept and formulas. Okay. So, yes, Saurabh Chaudhary will be discussing the Rankine cycle after this refrigeration air conditioning. Okay. Now, next is adiabatic or adiabatic humidification or saturation process or chemical process. Chemical dehumidification or adiabatic humidification. What is the meaning of this thing? Adiabatic means as constant enthalpy. At constant enthalpy, if you increase the moisture or decrease the moisture, that is called adiabatic humidification or adiabatic dehumidification. Adiabatic dehumidification is also called as, it is also called chemical humidification or dehumidification. What is the meaning of chemical humidification or dehumidification? When we'll use some chemical like silica gel or some other absorbent so that this moisture can be increased or decreased, that is called as chemical dehumidification. So under adiabatic chemical dehumidification, certain chemicals like silica gel, alumina are used to absorb the moisture. That is called as chemical dehumidification. And what is the meaning of adiabatic humidification or dehumidification? When at constant enthalpy, this is the constant enthalpy line, at constant enthalpy if you increase the humidification, if you do increase the moisture or decrease the moisture, that is called adiabatic humidification or dehumidification. But chemical dehumidification means using some artificial chemicals to provide dehumidification or absorb the moisture. Okay. And now there is another term called bypass factor and psychrometry. Bypass factor represents the total air supply to the cooling coil which remains uncontacted with the coil and bypass it. So basically, in the case of air conditioning, what will happen is, in the case of air conditioning, the cooling, there is a coil which is also called cooling coil or heating coil, depends on the purpose, whether you have to maintain the room at low temperature or high temperature. Okay, so suppose this coil are called as bypass factor of heating coil and cooling coil. What is the meaning of bypass factor? Bypass factor means when the air will pass through the coil, some amount of air will remain uncontacted. Some amount of air will pass through the coil which will not come in contact with the coil. That is called as bypass factor. The uncontacted air which will not come in contact with the coil is called bypass factor. So this bypass factor is equal to, of a heating coil, it is defined. Suppose you have to find the bypass factor of heating coil. So you can see, suppose this is a heating coil. Inlet temperature is T1. The coil temperature is T3. And this temperature is T2, outlet temperature T2. So it's obvious that it is a heating coil. So this temperature, that is the coil temperature, will be greater than this temperature and inlet temperature will be lowest. So since it is a heating coil, coil temperature will be highest because it is a heating coil. Okay. So if you have to find the bypass factor, it is equal to, you have to remember the formula, bypass factor of heating coil will be equal to T3 minus T2 over T3 minus T1. That is the formula for bypass factor. So you just have to take these three temperatures in this order: highest temperature, medium temperature and lowest temperature, and it will be T3 minus T2 or T3 minus T1. That is the bypass factor of heating coil. And there is also a term called efficiency of the coil. Efficiency of the coil is equal to 1 minus bypass factor. If you have to find the efficiency means how much efficient is this coil. Okay, so for that, efficiency of the coil is equal to 1 minus bypass factor. That is the formula for efficiency of the coil, 1 minus bypass factor. Okay, now if you have to find the efficiency of bypass factor of the heating coil, so how we can use this formula to find the bypass factor of the cooling coil? We know that for a cooling coil, suppose what will happen to the cooling coil? Suppose this is a cooling coil. obviously, suppose this is T1 temperature, this is T3 temperature, this is T2 temperature. It is quite obvious if it is a cooling coil, so T1 will be highest, then T2 will be, this will be the temperature variation for a cooling coil, right? Now, if you have to find the bypass factor of this cooling coil, then what will happen? If T1 is higher than T2 than T3, so it will be equal to, bypass factor will be equal to, since T1 is higher than this will be equal to T2 minus T3 over T1 minus T3. That is the formula for bypass factor of the cooling coil. Again, if you have to find the efficiency, it will be equal to 1 minus bypass factor. That is the formula for efficiency. Now, what is important again, sometimes they will give you more than one coil, and if you have to find the bypass factor, suppose the bypass factor of single coil, you know the bypass factor of single coil. So, bypass factor of n coil can be found by this formula. If bypass factor of single coil is equal to x, and if you have to find the bypass factor of n coil, then the formula will be equal to x power n. If bypass factor of a single coil is equal to x, the bypass factor of the n coil will be equal to x power n. So, if I ask you a question, suppose bypass factor of single coil is equal to 2. So, what will be the bypass factor of 3 coils? Tell me quickly. Tell me quickly. Gurpreet is having this question, what is the definition of entropy, definition of entropy I have told you in this topic of thermodynamics revision part 2, I think you can see, look it from there, okay. And you are asking about modified Rankine cycle. Modified Rankine cycle is basically some modification we do in the Rankine cycle. Don't worry, I'll be telling you about this thing after this we'll be studying Rankine cycle, so I will tell you what is modified Rankine cycle, okay. Yes, so answer will be 8. So if bypass factor of 1 coil is 2, so bypass factor of 3 coil will be 2 power 3, because the formula is this, okay. Now the last topic is mixing of air stream. Sometimes what will happen in the case of refrigeration air conditioning, what will happen, sometimes they will ask you the mixing, this question comes from mixing of air stream. So in the refrigeration, in the air conditioning, what happens, two airs mix together to give the cooling air, right? That is happening in the coil also. We'll have 3 air stream. One is at the inlet of at temperature T1. Suppose this is at temperature of T3 and this is temperature of T2. So whenever you will achieving this air conditioning process, we'll have some mixing of air stream. There will be mixing of the air. Air stream is air particles. Okay, so there will be mixing of the air particles. So there is a direct formula for mixing of the air particle. What will happen when mixing will take place? Suppose this is the stream 1, this is stream 2, and this is stream 3, final stream 3. So when mixing will take place, what will happen? The total mass M1 plus M2 will be equal to M3. Okay, or final mass of the third air stream will be equal to sum of the mass of the first 2 air stream. So that will be the total mass. But for the enthalpy, specific humidity and temperature, the formula is this. It will be equal to M1 into H1 plus M2 into H2 will be equal to M3 into H3, where M3 is equal to M1 plus M2. M1 into W1 will plus M2 into W2 will be equal to M3 into W3, okay, where M3 is equal to this. So this formula can be you can use for mixing of the air stream, okay. Next is these are some important points that I have to tell you for revision. These are important notes. See, cooling and dehumidification process is possible when the cooling coil temperature is less than the dew point temperature of the entering coil. So this cooling and humidification is possible only when the cooling coil temperature, coil temperature becomes less than the dew point temperature, then only you can achieve cooling and dehumidification. Okay, so these are some important points. During heating and humidification, dehumidification, the dry bulb temperature increases and specific humidity decreases. That is quite obvious. When heating and dehumidification both take place, so dry bulb temperature will increase and specific humidity will decrease. Example of heating and humidification. This is quite, sometimes it is asked as a theory question. Example of heating and humidification is steam spray in air. So if it is a normal air and if we spray the steam into the air, it is not only just going to increase the temperature of the air, it will also reduce the moisture. So that is why steam spray in air is an example of heating and humidification. And in the case of a desert cooler, we have cooling and humidification. And what happens in your air conditioner? In the air conditioner, we achieve cooling and dehumidification, both. In the desert cooler, we have cooling and humidification. And in the air conditioner, we achieve cooling and dehumidification. That is why it is recommended to put the desert cooler outside your room so that humidity cannot be increased in the room. Okay. So why desert cooler are kept outside the room? So that humidity of the room should not increase. Okay. Because desert cooler are based on cooling and humidification. And for effective, desert cooler are more effective when the value of wet bulb depression is high. When wet bulb depression is high, then desert coolers are more effective. Okay. The last topic is ventilation air. So what is ventilation air? Ventilation is basically maintaining the quality and purity of the air. That is called ventilation air. So what is ventilation air? Generally, you know that human beings feel comfort between 24 to 26 degrees Celsius diurnal temperature with 50 to 60% relative humidity. This is the temperature and relative humidity at which human beings feel comfort. Okay. Now, so you just have to understand this thing. What is ventilation air? Human beings feel comfort at the dry bulb temperature of, normally in your air conditioner, we just need to maintain temperature of 25 degrees Celsius and you will feel comfort, right? And relative humidity or the moisture that is required to be maintained for the comfort of the human being is 50 to 60% of relative humidity is required. That is the comfort condition. This is also called comfort conditioning. Okay. Now, what is ventilation air? Ventilation air is the fresh air that is supplied to the air conditioning equipment in order to maintain its purity. That is called as ventilation air. Okay. In the operation theater, in your operation theater, when operation, you know that in the operation theater, 100% fresh air is supplied to maintain the purity of the air. 100% fresh air is required in the operation theater. In summer air conditioning, we use cooling and dehumidification, whereas in case of winter air conditioning, we use heating and humidification. So this is important. So this is the last important thing of refrigeration and air conditioning subject. So with this, I complete the revision of refrigeration air conditioning. Now in next 20 minutes, we will cover the revision of power plant subject. So let's go to power plant subject. So before I tell you the power plant, let's have you can take a break of 1 minute. Okay. Now, so if you talk about the gate exam, in the gate exam from the power plant subject, we have some important topics like Rankine cycle, Brayton cycle, air compressor. These are some important topics. I am going to revise these two topics, Rankine and Brayton cycle. Okay. So in the Rankine cycle, what is Rankine cycle? It is the ideal working cycle of a steam power plant. Now this is ideal Rankine cycle. Like Guruprad was asking this question, what is modified Rankine cycle? Modified Rankine cycle is basically, it is a simple ideal Rankine cycle, but with some modification. We require some modification to be done in the Rankine cycle so that efficiency of the Rankine cycle can be increased. So that is called modified Rankine cycle. And how the efficiency can be increased? With the help of a regeneration or regenerator. Okay, so if we are using a reheater and regenerator in the Rankine cycle, that is called as modified Rankine cycle. So this is the ideal Rankine cycle. It basically contains 4 basic components. We have this boiler, turbine, condenser and pump. And this acts in a clockwise direction. So the Rankine cycle is the ideal cycle for all the steam power plant. For steam power plant, the ideal cycle is called Rankine cycle. Okay. So what happens in the Rankine cycle? We have the compression take place in the isentropic compression take place in the pump. Then this water goes into the boiler. In the boiler, heat is supplied. Okay. And due to supply of the heat in the boiler, the evaporation phenomena take place and the water changes into steam. This steam goes into the superheater. It is not shown here. It goes into the superheater, and from there, superheater steam goes into the turbine. Now this superheater steam will rotate the blades of the turbine, okay, which will produce the power output, because the shaft of the turbine is connected to the shaft of the generator. Okay. Now the steam at the exit of the turbine goes into the condenser. Condenser is a heat exchanger which will reject the heat of the steam, okay, and also the condensation phenomena will take place. The condensed water will go into the pump, and this is how the cycle is maintained. Now the Rankine cycle is shown on the temperature entropy diagram. It looks like this. Okay, so firstly we will have isentropic compression in the pump, then we will have constant pressure heat addition in the boiler, then we will have 3 to 4 is expansion, isentropic expansion in the turbine, and then we will have constant pressure heat rejection in the condenser, and again, so these are the 4 processes in the steam power plant or Rankine cycle. Okay. Now if you have to find the efficiency of this Rankine cycle, what is efficiency? Efficiency is equal to work done over heat supplied, right? Work done over heat supplied is the formula for efficiency. Now if you have to find the efficiency in terms of work done will be equal to net work over heat supplied. What is the net work? It is equal to turbine work minus pump work over heat supplied. So you have to remember this formula of efficiency for the Rankine cycle. It is equal to net work, that is turbine work minus compression work. Now my question is, why I am writing turbine work minus compression work? The reason why I am writing turbine work minus compression work, because in the case of a Rankine cycle, turbine work is more as compared to pump work. And turbine work is a positive work, right? Steam power plant is a cycle which produces the work. That is why the net work will be equal to turbine work minus pump work. Now this turbine work is a positive work, pump work is a negative work, but this pump work is very, very small as compared to the turbine work. That is why the net work is equal to turbine work minus pump work over, and the efficiency is equal to net work over heat supplied. Okay. So if you have to find the formula of efficiency, or if you have to calculate the efficiency, you just have to find the turbine work, pump work and heat supplied. Okay. So if you want to apply the formula in terms of enthalpy, this will be equal to, suppose the enthalpy is H3, that will be H3 minus H4 over what is the pump work, that is equal to H2 minus H1 over heat supplied is equal to H3 minus H2. So in terms of enthalpy, this is the formula for efficiency of the Rankine cycle in terms of enthalpy. Okay, so sometimes, mostly in the most of the times, the enthalpy will be calculated with the help of efficiency will be calculated with the help of enthalpy. So enthalpy values will be given to you at different temperature of turbine and condenser and pressure, boiler and condenser pressure. The temperature, at this temperature, the enthalpy values will be given to you in the exam. Okay, and you just have to apply the formula. Yes, Saurabh Chaudhary, what is the question? I am not able to understand. Rankine cycle, reheat and regeneration. See, don't just be patient. I am coming on that. See, I cannot jump onto some topic directly, right? I'm just revising all the topics, okay? So I will be coming on reheat and regeneration. Please be patient, okay? So in the exam, you just have to apply this formula and you will get the answer. You just have to apply the formula of, this is H3 is the enthalpy at the inlet of turbine, H4 is the enthalpy at the exit of turbine. And so what is tricky in the exam? Sometimes they don't give you the value of, they don't directly give you the value of enthalpy. Okay, you have to find this enthalpy. Okay, so how you can find the enthalpy? Sometimes this 0.4 will be in the wet region, that is at this region. So you can find the value of enthalpy by using S3 is equal to S4. Why? Because the expansion in the turbine is isentropic expansion, so you can use this S3 is equal to S4. Okay, this value will be definitely given to you for superheated region. So that will be equal to S3 will be equal to SF4 plus X times of SFG4. By using this formula, you will get the value of dryness fraction at this point, and the enthalpy of this in the wet region will be equal to H4 will be equal to HF4 plus X times of HFG4. So from here you can find the enthalpy in this region and you can find the answer. Okay, so this is something that you have to be careful in the exam while solving the numericals of Rankine cycle. Sometimes directly value will not be given to you for enthalpy at all the points. Maybe you have to use this formula to find the dryness fraction, and from dryness fraction you can find the enthalpy at this point, and then you can easily solve the question. Also sometimes pump work is not given to you. Okay, so pump work direct formula is equal to, for pump work, the direct formula is specific volume into boiler pressure minus condenser pressure. This is the formula for pump work. It is equal to boiler pressure, specific volume at the entry of the pump into boiler pressure minus condenser pressure. So from here you can also find the pump work. This is also a formula that normally we use in solving the numericals of Rankine cycle. Okay. So if you do energy analysis, already I have told you this formula. It is equal to S3 minus H4 minus H2 minus H1 over S3 minus H2. So already I have told you about this. Let's move further. Now, deviation of actual vapor cycle from ideal cycle. So that was ideal Rankine cycle, but actual in the actual power plant we don't have ideal Rankine cycle. Sometimes due to irreversibility in the operation or due to friction or due to temperature difference, the cycle is not ideal cycle. We have some irreversibility in the power in the turbine and compressor. Sorry, in the turbine and pump. Okay, so to accommodate those irreversibility, what will happen? We have to use this isentropic efficiency. Isentropic efficiency, I have already told you this thing. Isentropic efficiency will be using for both turbine and as well as the pump. For the pump, isentropic efficiency for a pump is equal to isentropic work over actual work. And isentropic efficiency of a turbine is equal to actual work of turbine over isentropic work. So we'll be using this efficiency. Most of the time the question in the Rankine cycle are very easy, but they don't make it easy, they make it complicated by giving you the value of isentropic efficiency. Okay, so if isentropic efficiency will be given to you in the exam, in that particular case, you cannot directly find the efficiency like by using that formula. You cannot directly find the efficiency. You cannot directly find the efficiency by using this formula. In that case, you cannot use these enthalpy values. In that case, you have to find the enthalpy of the actual process. This is isentropic. But for actual, if isentropic efficiency will be given to you, you have to find H4 and H2. H1 and H3 is going to remain same. They will be same. But if isentropic efficiency will be given to you in the exam, in that case, you have to find the actual enthalpy at the exit of the turbine and actual enthalpy at the exit of the pump. And how you can find that? You can find that with the help of this formula which are given here for isentropic efficiency of the pump and turbine. So when isentropic efficiency of the pump and turbine will be given to you, you just have to use this formula. It will be H2S. H2S means enthalpy at the exit of the turbine when pump when the isentropic process take place. H2S minus H1 divided by H2 minus H1, and for the turbine it will be H3 minus H4 over H3 minus H4S. Okay. So this formula will be using. So do remember this formula, because if whatever I have told you in theory, that is important, but actually you have to solve the numericals. From Rankine cycle, question comes in the exam, numerical comes. Okay, so you have to understand how to tackle with the numericals also. I will not be able to practice the question here live in the class because the time is very less for us. So, but I can tell you the concept, what you have to use. Whenever isentropic efficiency is given to you, you have to find these values with the help of these two formula. Okay, and these two formula will also be used for the Brayton cycle, because in both the cycle, Rankine cycle and Brayton cycle, actual efficiency is different as compared to, actual work is different as compared to isentropic work due to irreversibility. So these formula will be used for Brayton cycle also. So you have to remember this formula. Now ideal reheat Rankine cycle. So this is ideal reheat Rankine cycle. Now you like Guruprad was asking that is there any modification that we do in the Rankine cycle? Yes, we give two modification. We do two modification in the Rankine cycle. First modification is reheating, other is called regeneration. What is reheating? Reheating means I have told you this thing that in the case of a turbine, in the case of a Rankine cycle, at the exit of the turbine, the vapor, the steam that goes at the exit of the turbine is in the wet region. It's normally in the wet region. Suppose it is in this region. Okay, but we don't want the steam to be in the wet region. Why? Because it can cause erosion of the blades of turbine. So we always want that our steam at the exit of the turbine should be having higher dryness fraction or less moisture. So to remove the moisture at the exit of turbine, we perform the operation of reheating. What is reheating? The steam which is coming at the exit of the turbine after expansion, we will again reheat. Okay, we will again heat that steam and again we'll send that steam back to another turbine for expansion work. After that, the steam which will come out at the exit of that turbine, it will go into the condenser. That is the whole scenario of reheating. So only purpose of reheating on the Rankine cycle is to increase the dryness fraction The only purpose of using the reheating in the Rankine cycle is to increase the dryness fraction. See, why I am repeating it again? Because sometimes in the theory question, it is asked in the exam that does reheating increases the efficiency of the Rankine cycle? No. It has nothing to do with the efficiency. Reheating has nothing to do with the efficiency. It has only to do with the dryness fraction. Dryness fraction will increase or the moisture will decrease. That is why we use reheating in the Rankine cycle. That is the only purpose. And for that, we just have to use a reheater and two turbines. We'll be using a reheater between two turbines. That is the only thing that you have to do. Nothing, no other modification has to be done. Okay. So what we'll be doing here is, there will be a pump. This pump will pump the water into the boiler. The steam will go into the high pressure turbine. From the high pressure turbine, the steam which will take the steam from the high pressure turbine, it will send the steam to a reheater. In this case, the boiler will again be taken as a reheater. So this steam will again go into the boiler. This will get again heated up. Okay, and with the help of this heating, the moisture will get removed. Now this removed moisture steam will again go into the low pressure turbine. Now this low pressure turbine will perform the action of producing the actual turbine work. Okay, and then the exit of the low pressure turbine will be sent to the condenser and the whole process will be same. Okay, so if you see this process on the TS diagram, 3 to 4 is 3 to 4, this 4 will be here. 3 to 4 is the high pressure turbine, expansion in the high pressure turbine. Then 4 to 5 is reheating process. Again we are reheating. So this is heating, one heating, then we are again it is reheating. And then this is low pressure turbine expansion. So what will be the change? If the expansion is only by this turbine, then at the exit of the steam will be at this point. Now you can see this is a wet region. This is called wet region. If the expansion take place, if the expansion of the steam take place in the wet region, it is going to cause erosion of the blades of the turbine. So to avoid that thing, we will do reheating. And it will be very good if we can increase this temperature. If this temperature of addition is called mean temperature of heat addition. If we increase the mean temperature of heat addition, we can also increase the dryness fraction. So there are two changes of reheating. One is increase of dryness fraction, other change is increase of mean temperature of heat addition. Nothing, no other change. So if we have to find the efficiency of this reheat cycle, efficiency will be equal to, the net turbine work will be equal to H3 minus H4 plus H5 minus H6 minus pump work. So this is the total turbine work. Okay, and pump work will be equal to minus H2 minus H1 divided by what will happen through the heat. It will be equal to H3 minus H2 plus H5 minus H4. So both turbine work and heat supplied will increase. So we cannot say that reheating will increase the efficiency. Efficiency does not increases with reheating. Why? Because both turbine work and heat supplied will increase. So efficiency does not increases. We can say that with a single reheater, efficiency can be increased by 4 to 5%. Only 4 to 5% increase in efficiency take place. But in the actual power plant, we don't use a single reheater, we use more than 2 reheaters. So if we increase the more than 2 reheaters, then what will happen? The efficiency will decrease. So that is why we cannot say that with reheating, efficiency increases. It does not increases, only changes increase of dryness fraction and increase of mean temperature of heat addition. Okay, so this is about reheating. Next is regeneration in the Rankine cycle. What is regeneration? In the regeneration is a process which is used to increase the efficiency. Regeneration is the only process which is used to increase the efficiency. Either it is a Brayton cycle or it is a Rankine cycle. You just have to remember, if regeneration term is mentioned, then only we have to we can say that efficiency will increase. If regeneration is not there, efficiency will not increase. Okay, that is the only thing that you have to remember. Okay, so how does regeneration take place in the Rankine cycle? Regeneration, like say regeneration, something is regenerated. What is regenerated? We are actually in regeneration, efficiency is increasing because efficiency is equal to net work over heat supplied. So this net work is kept same if heat supplied is reduced. Or even if it is not same, if heat supplied is reduced, then efficiency will increase. So in regeneration, we will reduce the heat supplied. Now where is heat supplied? In the boiler. So if we can reduce the heat which has to be supplied by the boiler, we can increase the efficiency. How we are increasing the efficiency? We are reducing the heat supplied. So what we'll do here, for the purpose of regeneration, we'll perform the process of bleeding. So that bleeding term is only used in Rankine cycle. Bleeding means extracting of the steam, during expansion of in turbine. Extracting the steam during expansion turbine is called as bleeding. So bleeding basically means in the Rankine cycle that we extract some amount of heat, some amount of steam during expansion of turbine, and we will give this steam to the boiler. To the feed water heater. What is feed water heater? Feed water heater is that a heat exchanger in which we supply the feed water. The feed water will not directly go into the pump in the boiler. Normally what happens? The pump will directly send the water to the boiler. Okay. So what boiler has to do? Boiler will increase the temperature of the feed water from 20 degrees Celsius to 100 degrees Celsius or more than 100 degrees Celsius so that it can be converted into steam. But imagine this thing, if the temperature if the feed water is already having temperature of 50 degrees Celsius, so less heat has to be supplied by the boiler. So this temperature of feed water is increased with the help of a feed water heater. And what is the source of the heat for feed water heater? The source of the heat is the steam that we take from the turbine. So we will take some steam from the turbine and we will give this steam to the feed water heater, and this feed water heater will heat the feed water coming from the pump 1. So this is the pump 1. This will send the feed water to the this open feed water heater or feed water heater. Okay, and this feed water will heat the feed water from the first pump. Okay, it will get heated up, and the heated feed water will go into the boiler. Okay, so that is how we can reduce the heat which has to be supplied in the boiler. Okay, the heat which has to be supplied in the boiler will be reduced. Okay, now this is the whole process of regeneration. Okay, so if you apply this feed water heater, suppose we can say that 1 kg of steam goes from the boiler to the turbine, and we are taking y kg of steam. We have sent this y kg of steam to the feed water heater. So leftover 1 minus y kg of steam will go into the condenser, right? So let us say that at 0.5, at H5 enthalpy, 1 minus y kg of steam goes here, and at y kg of steam goes at point 2, S2, and what is coming out? It is coming out that 1 into 1 kg of steam at S6 is coming out. So if you apply the heat balance equation, it will be H5 into 1 minus y plus H2 into y is equal to S6, or it will be equal to H5 minus y times of H5 plus H2 y times of H2 is equal to S6, or it will be equal to y times of H2 minus H5 is equal to S6 minus H5. So y will be equal to, from here the y, the amount of steam which we have bled is equal to S6 minus H5 over H2 minus H5. Okay. So in the exam what will happen, we have to, what is the difference between closed and open feed water heater? Only difference between closed and open feed water heater is that closed feed water heater, open feed water heater, there is a direct mixing of the steam and the feed water, but in the closed feed water heater is a kind of a heat exchanger. It is a kind of a shell and tube heat exchanger in which the water will be sent to the tubes of the heat exchanger of the feed water heater, and the steam will be supplied to the shell, so that there is no direct mixing of the feed water and the steam in the closed feed water heater. So in the closed feed water heater, there is no direct mixing of the steam and the feed water, but in the open feed water, there is a direct mixing of the steam and the feed water. Okay. So if you have to solve the question of Rankine cycle with regeneration, you just have to find the value of y that will be equal to, that can be solved with the help of a heat balance equation, energy balance equation. Okay. So efficiency will be equal to turbine work, which will be H1 minus H2 plus 1 minus y times of H2 minus S3. Okay. Minus pump work, which will be equal to 1 minus y of H5 minus H4 plus S7 minus S6 divided by total heat supplied, which will be H1 minus S7. Okay. So that is how you can find the efficiency. Now I think I have taken already a lot of time. So I'm so sorry, and this is sorry that I'm actually saying that, because I thought I will be able to complete Brayton cycle also, but we don't have much time left. Okay. So we have revised the complete thermodynamics, IC engine, refrigeration, air conditioning and power plant subject up to Rankine cycle. And so this was the last class, so I won't be able to revise the Brayton cycle. But what I can tell you is, in the Brayton cycle also, you have to remember the formula of efficiency of the Brayton cycle. The efficiency of Brayton cycle is equal to 1 minus RP, that is pressure ratio gamma minus 1 over gamma. You have to remember this formula for efficiency of the Brayton cycle. Okay. So I am falling short of time, so I am just telling you like this quickly. So back work ratio is a formula you have to remember for Brayton cycle, that is equal to compressor work over turbine work, or it is equal to ratio of negative work over positive work. So you have to remember this formula. Okay. And work ratio is equal to net work over positive work. That is the formula for work ratio. It is also equal to 1 minus back work ratio. You have to remember this formula. Okay. There is also a formula for optimum pressure ratio. Optimum pressure ratio is equal to T3 over T1, gamma over 2 times gamma minus 1. T3 is the maximum temperature, T1 is the minimum temperature, gamma is the adiabatic index. So you have to remember this formula for optimum pressure ratio. It is for a single stage compressor. For a two-stage compressor, this is it is equal to T maximum or T minimum over gamma over 2 times gamma minus 1. And if efficiency of the turbine compressor are given to you, in that case optimum pressure ratio is equal to efficiency of the compressor into efficiency of the turbine into T3 over T1 gamma over 2 times of gamma minus 1. Okay, so sometimes if efficiency, isentropic efficiency of the compression turbine will be given to you, so you have to use this formula of optimum pressure ratio. But if it is not given to you, so the formula of optimum pressure ratio is this. That is maximum temperature over minimum temperature power gamma over 2 times gamma minus 1. Okay. Now there is also formula for maximum work output in Brayton cycle. Maximum work output in the Brayton cycle is achieved at optimum pressure ratio, which is equal to T maximum over T minimum gamma over 2 times gamma minus 1. Okay. Understand? And what is the formula for maximum work? It is equal to, I think it is equal to T maximum minus under root T minimum whole square. That is the formula for maximum work output. And this maximum work output is achieved at optimum pressure ratio, which is equal to T maximum or T minimum gamma over 2 times of gamma minus 1. Okay. Brayton cycle with regeneration. So like in the case of Rankine cycle, if we do some modification in the Brayton cycle also, these modifications are reheating, intercooling and regeneration. So I am going to tell you some important points. You just have to remember that for a Brayton cycle, efficiency only increases with regeneration. Reheating and intercooling has nothing to do with the efficiency. It is not going to increase the efficiency. Efficiency decreases with intercooling and reheating in the Brayton cycle. But if we use with this intercooling with regeneration and reheating with regeneration, then efficiency will increase. Okay. So with regeneration, what is the formula for efficiency of an ideal regenerative cycle in the case of a Brayton cycle is 1 minus T1 over T3 Rp over gamma S1. So the formula of efficiency of an ideal regenerative cycle is one minus T1 T minimum over T maximum into Rp over gamma minus 1 over gamma. This is the formula for ideal regenerative cycle. You have to remember this formula. It is very, very important. Okay. And what is the effect of regeneration? There is no change in the compression turbine work output in the Brayton cycle. Okay. Net work output remains same. Both heat supplied and heat rejected decreases. Mean temperature of heat addition will increase. Cycle efficiency will increase. So the effect of regeneration is that cycle efficiency will increase with regeneration. What is reheating? Reheating is same. What we do in the case of a Rankine cycle, the same is reheating. But here the purpose of reheating is different. Here we are not using a reheating for increasing the dryness fraction. We don't require any increase of dryness fraction because we are using air or gas as a working fluid. So what is the purpose of increasing the reheating? Here in the case of Brayton cycle, reheating is only done to increase the turbine work. So to increase the turbine work, reheating is done. So at constant compressor work, turbine work is increased. But when we increase the turbine work, heat supplied will also increase. So efficiency will decrease. So that is the effect of reheating. So in the reheating, what we do? Between two turbines, we will use a reheater so that turbine work can be increased. Okay. So what is the effect of reheating? No change in the compressor input work. Turbine work increase. Net work output will increase. Okay. And efficiency of the cycle will decrease. Okay. So with reheating in the Brayton cycle, efficiency will decrease. What is intercooling? Intercooling and reheating both are the two ways in which we can increase the net work output of a Brayton cycle. Net work means turbine work minus compressor work. So if we have to increase the net work, there are two ways. Either is decrease the compressor work or increase the turbine work. Turbine work is increased by reheating and compressor work is decreased by intercooling. But these two ways, both the two ways will decrease the efficiency. That is why we don't use intercooling and reheating single. We use combine them with regeneration so that efficiency can also increase. Okay. So this is the effect of intercooling. You can see decrease in compression work, no change in turbine work, net work will increase, and so efficiency of the cycle will decrease. So that is all in the lecture of this. Now before we complete the session, so with this I complete the revision part of thermodynamics and applied thermodynamics. It was very difficult for me to cover everything in 3 classes. Okay, but because we have to cover all the revision of all the subjects in 20 days, so that is not possible for me to take more than 3 classes. Okay, so whatever we have revised in 3 days, I hope you understood. Okay, if you have any problem, please let me know in the comment box. You can ask me the question in the comment box. Okay, now this is very important information. The Gradeup has launched a course called Vision 2021 for those aspirants who are in the B.Tech 3rd year. Okay, so it is only for those students who are in the B.Tech 3rd year or B.Tech final year. Those who want to prepare for GATE 2021 and ESC 2021, Gradeup is providing a complete full course for ESC prelims paper 1 and 2 and also for conventional and for GATE 2021. Okay, so it is only for GATE and ESC 2021. In this we are going to provide 550 plus hours of live classes with proper study notes and quizzes for each classes. Okay, we'll also provide the 7,000 plus quizzes and conventional assignment for practice. okay, for ESC paper, mains exam. We'll also provide you full-length mock test and live evening classes. The main highlight of this course is that the classes will take place in the evening, that is after 7 p.m. Okay, so that the students who are attending any college, who are in the B.Tech or in the college, or those students who are working professional, they can attend the live classes in the evening. Okay. This is again a very important information. Those students who wants to take our Gradeup test series, you don't have to purchase a separate test series. You can purchase our Gradeup green card. In the Gradeup green card, we offer you two packages. One is yearly card, other is monthly card. In the yearly card, we will provide you, it is at the cost of 499 rupees. Okay, and monthly card is at the cost of 299 rupees. So in this, by purchasing this yearly and monthly Gradeup green card, what you can do is, you can practice all the mock tests in the complete year if you purchase this yearly card, and if you purchase the monthly card, you can practice all the mock tests in that complete month, which have been provided by Gradeup. Whether it is for ESC exam, or it is for GATE exam, or it is for SSC exam or ISRO exam, if any mock test is provided in the by Gradeup, you can attempt all the mock tests in that particular year or month. Okay, so the cost is given here, so you can purchase this cost, this Gradeup green card. So that is all the information that I have to tell you, and I hope you see. I'm very sorry if I was not able to cover any concept or not able to revise any concept. Well, I have tried to cover all the concept of thermodynamics, IC engine, refrigeration, air conditioning, which is important. But I can yes, I can say that I was not able to cover power plant by in that required time, because the time was very less. So, but still I have tried to cover all the important topics from the complete thermodynamics and applied thermodynamics for revision of GATE 2020. So I hope you have understood that. Okay, and yes, Pranav Chaudhary, we are going to, this is called as Score Booster Series for GATE 2020, where we will be revising all the subjects of mechanical for GATE 2020. And this revision these classes are going from the last 3 days. Okay, and in the last 3 days, we have covered subject of thermodynamics. Now from tomorrow onwards, we are going to start another subject. Okay, so those students who are preparing for the GATE exam from the last 1 year, 6 months, 2 months, 3 months, and who have to write their exam on 1st of February. So we are providing these free classes for revision, especially for those students, so that you can revise the concept, you can revise the important formulas. Okay, and what you can do now is you can practice all the important questions of thermodynamics and applied thermodynamics. Okay, you can take our Gradeup green card also. You can take our Gradeup mock test also, and do practice the mock test, or especially full length mock test, because it's the time for full length mock test. After revision, you should practice the full length mock test. Okay, so that is all in the session of thermodynamic revision. With this, I complete the revision of subject of thermodynamics, and so if you have any query, you can ask your query in the comment box. Okay, and so I will meet you in the revision of subject of fluid mechanics and machinery on I think from 15th of January. Okay, and before that, some other faculty will take revision of other subject. Okay, so I'll see you on 15th of January. Till then, thank you and have a good day. Thank you. Don't forget to subscribe the channel and press the bell icon, because then only you will get the notification of our videos and about our session that we conduct on the YouTube channel. Okay, so don't forget to subscribe the channel and press the bell icon. And also you can share about this Score Booster series, which we are providing by Gradeup, to your friends and your colleagues, so that they can also get benefited by our Score Booster series for GATE 2020 revision. See you on 15th of Jan. Till then, thank you and have a good day. Thank you. Bye.